Pendulum motion. The swinging of a pendulum is an example of periodic or repeating motion. Periodic motion exists everywhere in the physical world, from the swaying of trees in the wind to mass and spring systems, physical waves on the ocean, or the rotation of a wheel. These are all examples of periodic motion. Today we're interested in simple harmonic motion, or rather periodic motion in which the time to complete a full cycle, the period, is a constant. For small displacements, the pendulum experiences a linear restoring force. This linear restoring force has the form of force is equal to minus some constant c times the displacement. Notice here I'm using c rather than the traditional k. Force equals minus kx is associated most often with a mass in a spring, but we're going to be seeing a slightly different form. So I'm going to leave it as c for right now. This is called Hooke's law, and any object subject to such a force will execute simple harmonic motion. This is a graph of the function force is equal to minus some constant times the displacement. Notice that the minus constant, this is the slope of a line, and we have a negative slope to our graph. If we look at the displacement, 15 units positive displacement, we follow the green arrow down and the red arrow over, and we read off the resulting force. Again, a minus 10 displacement. We follow that up to the graph, the red line over, and we read off the resulting force. Notice that when the displacement is negative, the resulting force is positive. This points the system back toward an equilibrium position. If the displacement is positive, the resulting force is pointed in a negative direction, again back towards some equilibrium position. The constant period of a pendulum in motion gave humans the means to measure small intervals of time. A second of time measured on one day is now equal to a second of time measured on another day. Kinematics, the study of motion, including distance, displacement, speed, velocity, and acceleration, these are all now possible. In other words, the beginning of physics. So we have Hooke's law, but we don't really have the equation of motion for the system yet. But we do know that force divided by mass is an acceleration. So let's go ahead and divide both sides of this equation by mass. Again, the force divided by mass is acceleration. This is Newton's second law. And we're going to absorb the constant divided by mass into something called omega squared. Notice that the acceleration and position have opposite signs. Acceleration is always back towards some equilibrium position. Later we'll see that the factor omega squared is the square of the angular velocity of the system. Angular velocity is measured in units of radians per second. Our ideal pendulum consists of a point mass on the end of a massless string. Of course, we don't have massless strings and we don't have point masses, but the approximation works. The moment of inertia of this object is simply the mass times the square of the distance from the center of motion. In this case, the distance from the center of motion is just the length of the string. The pendulum is going to experience non-constant angular acceleration. The angular velocity will change at various times at different rates. The parameters we have to work with this system are the length of the string, the mass itself, and the position at any particular time. Since the mass is confined to move on an arc, it's natural to think in terms of the causes of changes of angular motion. These are called torques. The first of these expressions is simply the cross product of a position vector and a force vector. This is simply how far from the center of motion and the perpendicular force is applied. The second is the moment of inertia times an angular acceleration. We'll express all of these in terms of the variables of our system. The moment of inertia here is simply mass times the length of the string squared times the angular acceleration. The second expression for torque is going to be the length of the pendulum times the force of gravity downward times the angle between the gravitational force and the position vector of the mass, and that's going to give us the perpendicular force, or the amount of force parallel to the actual motion. Let's go ahead and set these equal to each other and eliminate some common factors on either side. And we're left with alpha, or the angular acceleration, is equal to minus g over the length of the string times sine theta. This is the equation of motion for our pendulum. For large theta, this equation is nonlinear. In other words, the graph of sine theta is not a straight line. However, for small theta, we can make the approximation. Sine theta is about equal to theta. You can try this yourself. Go ahead and type in sine of 0.1 is equal to, and you'll read the answer off. Make sure your calculator is in radian mode. Once we make that approximation, we're left with an equation which is linear. We have an angular acceleration is equal to minus some constant, in this case g over L, times the position. This is the form of a simple harmonic oscillator. In this lab, you're going to have several objectives. You're going to investigate the effect of mass, length of the string, and the initial position on period of the simple pendulum. Seeing the equation of motion, can you already form a hypothesis? In other words, where do you see mass in this equation? What about the length of the string? Or the initial position of the pendulum? You're going to define period, frequency, and angular frequency. Period is the time to complete one cycle of the system. The units of period are in seconds. Frequency is the number of cycles completed in a given time. The units of frequency are inverse seconds or hertz. You've all heard of 60 hertz electrical power. That simply means there's 60 cycles per second. Angular frequency is measured in radians per second. This is also inverse seconds, but not hertz. These can be expressed in terms of one another with the equation below. The angular speed is equal to 2 pi times the frequency is equal to 2 pi divided by the period. You're also going to explain the limits of the linear approximation and the meaning of small displacement for this model. Again, we talked about sine theta being about equal to theta. Just make sure that your calculator is in radian mode when you do this. Lastly, you're going to calculate the acceleration due to gravity using a physical pendulum. We've already shown you that the angular speed squared is equal to gravitational constant divided by the length of the string, and the period is equal to 2 pi over the angular speed. With a little algebra, you can come up with an expression that involves the period, the length of the string, and the gravitational acceleration. Notice that if you have a stopwatch, you have access to the period. If you have access to a ruler, you have access to the length of the string. The only unknown left, then, is the gravitational acceleration. If you'd like to know more, you can consult Herbert Goldstein's Classical Mechanics. This was published by Addison Wesley. It's in its 3rd edition, and on its last publication was in 2001. I hope you enjoyed the presentation. Leave some comments, and I'll be sure to make more videos if you care for them.